I'll be starting off with the first segment in a computer vision part of the lecture series by Robotics Club. So I'll be talking about classical methods mostly, and then there would be a slight motivation for deep learning at the very end of this lecture. So when I talk about classical methods, I'm implying the methods which have been around us from the 20th century, methods which have evolved from the very start of cameras and pictures from the very get-go of it. That those operations like convolution and image processing were with us for a very long time, and like there was a lot of recent advancement as well. Like not to discount that these are ancient methods which have only existed in textbooks, these methods are still very relevant. And then for certain very advanced tasks like automatic classification, and for like something like categorizing objects, finding out what is that particular object, drawing bounding boxes around that object, for those very advanced topics, you would need certain methods which are called deep learning based methods. So just to give you a bit of backdrop about how this entirely new field of deep learning started, was that in 2012 there was this challenge called ImageNet challenge. So ImageNet is basically a data set comprising of a lot of classes. So there would be horses, there would be aeroplanes, there would be automobiles on it, and you want the computer to be able to automatically classify what that particular class is just by having that particular image of that class. So what happened in 2012 was that was the first time deep learning methods were employed to that task. They absolutely blew away all the other classical methods, and there has been an explosive growth in research into deep learning methods since that time as well, because they definitely showed that these methods have tremendously more utility, and basically able to beat other all the other classical methods on the accuracy on the metrics of that task. So, just to start with, into this broad field of computer vision, I want you to first understand about what exactly the computer has by itself to see the world around itself. So, what does a computer have? A computer has, like, there are other parts of it as well, like a lidar sensor, but we'll be talking about the camera sensor, which it has to develop an image of the world around it. When a computer has a camera and there's an environment outside it, lights of different intensities hit on the lens of the camera. They generate certain electrical signals which are converted to certain numbers by the computer, and those numbers comprise your images. So, like, look at this image of Abraham Lincoln. It's a rather blurred image, but I want you to focus on what comprises of this image. So there are a lot of numbers on the right image. There's 157, there's 153, 174. So what are these numbers? These numbers denote specific pixel values. So these pixels, when in taken in combination for the entire image, that pixel would form a matrix. So, like, I'm sure you would be familiar by now what a matrix is. So, like, if you understand matrices well, you would say that you can understand computer vision well. So, observe that all of these pixels have values ranging from 0 to 255, and basically all these values, different values from 0 to 255, give you different colors for that particular pixel. And when you have those specific colors, you would be able to form about what is the specific color of that pixel. And when all of those pixels are taken combined, you get the image which the computer is able to see. So, like, I want you to understand that the computer does not know that this is Abraham Lincoln, or I have to put black color here to like match the original image of Abraham Lincoln. The computer just has these particular numbers, and it is and just with these particular numbers, we're going to do all the image operations. We're going to do a very complicated task uh, 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 by working into computer vision algorithms. Like, just to talk about what is on the slide right now. So I've given you some examples of classical CV techniques. So basically, feature descriptors will be coming back to that in the next slide. This is task of object detection. So object detection is that if there's a human in the frame, you want the computer to know that there's a human in the frame. It should be able to tell you that, hey, you give it a photograph of a human in a particular picture, you want the computer to tell you, hey, there's a person on that image. So that is basically object detection. And in the recent years, there's been a lot of deep learning based methods like YOLO, you only look once, AlexNet, the one which I told you about, the method which blew away all the classical methods in 2012. These are deep learning based methods are a subset of the field of artificial intelligence, a very fascinating field. I'm sure some of you might have heard terms within these fields, and there's a lot to explore of computer vision in this particular field. So basically, when we talk about classical methods of computer vision, the first step which you want to study before you move on to before you move on to more advanced ways of using classical computer vision is to study image processing. So image processing is, put very simply, making certain changes to that input image matrix. Like this is your image matrix. I want to make certain changes to that matrix so that it is more useful to me. So like just a simple line, that is the entirety of image processing. I want to change this matrix in certain ways so that this matrix becomes more useful to me. So like try to think of what kind of changes might be more useful to it. So like a very simple example right now. I want to know where the hair of Abraham Lincoln is. So what would that mean? So like if you look into this picture too well, you would know that wherever there is black, there would be hair of Abraham Lincoln. Of course, for the eyes as well, there is black. But just ignoring that for right now, you would have an approximation by knowing wherever there's black, there's hair of Abraham Lincoln. So that is so if I have to like make that kind of change so that I am able to get that answer from my image, I need to make certain changes to me so that it becomes more useful to me. Um, Yeah. So try to think of methods about how we can do these kind of changes. So like one very simple example would be to like uh, you know about basic programming. I'm sure you there were early lectures on it. It would be to just run a for loop through the entirety of this image matrix. Try to ask every pixel, hey, are you black? You're not. You're 157. Hey, are you black? No, you're not. You're 153. So when you reach a certain pixel value, which would be exactly zero, that is what is black, and you know, hey, that's the black, that must be where Abraham Lincoln's hair is. So basically that is a kind of like way of moving pixel by pixel and trying to get the answers from those pixels about what makes the entirety of the image. So rather than just moving pixel by pixel, we want something more efficient. So think of something which could be more efficient than a pixel, working on a bunch of pixels, right? So how can we work on a bunch of pixels? We can do certain operations which would be called convolutions. So a convolution is a very crucial step in image processing, which is basically multiplying the input images by certain kernels. So kernels is just a fancy term for your matrix. It's just a simple matrix, and you have to multiply your input image by those matrices piece by piece. So what do I mean piece by piece? Is that imagine there's an identity matrix. So if I multiply my input by the identity matrix, so whichever portion of the input image I multiply this identity matrix by, I would get the original input image back. Therefore, the output image after this operation would also be my original image. So what say I multiply this reflection kernel? So if I multiply the reflection kernel, it would it would basically flip over the image. So like one intuition about why this would flip over image would be to like either you could try to multiply it out pixel by pixel, or if you really want to be sure of itself, try to think of that only the values on the center, that is one, would get retained in this sense, and the values on the corners are going to end up subtracting themselves when you multiply them, and then when you get a sum for it. So we'll be coming to convolutions and how to calculate it, but just try to think of it that the entirety of image processing is trying to make changes to a matrix so that that matrix becomes more useful to you. Right. So now we're on to some features. So features is basically a piece of information which is relevant for solving the computational task related to a certain application. So these features could be anything from an edge, from a corner, from a certain color, and you have certain detectors which are able to give that kind of information to you. So if I have an edge detector, it would tell me where all the edges are in that picture. If I have a corner detector, it would tell me where all the corners are in that image. So basically all these features, they are you get them after some kind of processing on that image, and that feature gives us very useful information about that image. For example, I give you an input image and I want you to build a program so that the computer is able to tell me uh, whether there's a box on it or not. So like just to give you more context, imagine there's a picture of a wall, and in the wall there's a door. I want you to make a computer program about whether there's a door on the wall or not. So one very easy way you could do that would be to just look at whether there are any edges in that picture or not. Because you know that if there's a door, there would be some kind of edges associated with the rectangle of the door. And if you're able to detect whether there are edges in that picture or not, you would be able to know whether there's a door or not. So like try to think of how these features might be useful to you, how they might be useful to a robot for solving its particular task, and try to always think back about how a human eye would see. Like it would be very trivial for you to see that, okay, I'm able to see that there's a black color door on this white wall, therefore there's a door over there. But for a computer, there's just numbers and matrices for it, therefore it has to like somehow make sense from that information. So you apply certain kind of image processing, you get that kind of an edge, and you know that, oh, okay, that there's a door over there, and therefore I can give that information back. To understand how from just numbers and matrices, we have now got something more definitive about that image, which we can utilize for solving some other task of a robot. Right. So convolution is a very crucial operation. So I talked about earlier as well. So there's a very hairy looking expression on a left column. You would see that it's computing two kinds of sums. So try to understand this by looking at this particular image. So like this red dotted matrix, you can see that 3 cross 3 very little one. So if you multiply that matrix layer by layer over the input image, you're going to get certain values. And note that this is not simple matrix multiplication, this is cell by cell matrix multiplication. So I don't want you to confuse your original intuition about what matrix multiplication is. This is just cell by cell. So like the first pixel of the kernel is multiplied to the first pixel of the 3 cross 3 layer you've chosen from the input image right now. So once you multiply it pixel by pixel, you would see that 245 is multiplied to 0, 248 multiplied to -1, 255 to 0. You get all these values, and when you sum all of these values, they become 192. And that is the value you assign to the value at the center of that layer, of that 3 cross 3 layer. So this is how you get the value of your convolution operator. So I've summarized it as well on the slide. So you place the center of the kernel on your pixel. You multiply each overlapping pixel and the kernel cell. You sum all of these products and assign the sum to the pixel. As simple as that. That is what the convolution operator is doing. So like observe that on multiplying this kind of kernel, the output image becomes more sharpened. So like how can you say that this is more sharpened? Observe that there are thick black lines which are able to denote where the man's face is, and there are thick white lines also. Like all of the colors have become more I would say more pronounced, that you would be able to easily distinguish that there's an edge between these, and that is going to like help you understand that this is a sharpened image from the original blurred image. Right. So after we've talked about these kernels, so we can move on to yet another basic feature extraction. So this is a toy example of finding the edges in an image. So observe that for different kernels, we're able to get different kinds of features. So a feature could be vertical edges, a feature could be horizontal edges. So when you multiply the kernel on the left to the input image, you get higher values for the vertical edges. So like what I mean by higher values is that all these white lines are the vertical edges in the frame. And on the right, the same holds for the horizontal edges. So like I want you to try to think of and develop an intuition about why these vertical edges are getting more visible in the output image. So observe that this kernel is doing two things. Firstly, it is giving a zero value to all the pixels on the center, and then it is giving equal and opposite values to the pixels on the left and right. So like there's one, there's -1, there's two, there's -2. So what happens is that it takes the difference between the left and the right, and that is going to give you a derivative. So like if you take the transpose of this matrix, you're going to get similar values for the horizontal. So like if this was not really clear right now, we'll be discussing in this in detail in the next two slides. So like just hold on. try to think of why this kind of matrix multiplication is going to give that kind of result to you. Mhm. So now we're going to look over edge detection in more mathematical detail. So edge detection. At this point, I've actually kind of run ahead without actually defining what an edge is. So I'll do that right now. So an edge is basically any change in the input image across any discontinuity or any sharp change, a very significant change which you can observe. That would be an edge. So like try to visualize how this is happening. So go over to that original example of a door on a wall. So what is the sharp change which is happening? So there's a white colored wall and suddenly there's a brown colored door. So what is changing across that wall and door interface? There's a sharp change of the color. So basically that uh, there's a discontinuity over there. So like the entirety of it was white and then it is suddenly black. So like edges are those kind of discontinuities, and to detect those kind of discontinuities would mean to detect those kind of edges. Basically, edge detection includes a variety of mathematical methods that aim at identifying points in an image at which the image brightness changes sharply, or more formally, has discontinuities. So, I want you to think of why detecting an edge is something which might be useful to me. So, let's try to think of an example of something a robot might do. So, I have a robot which has to solve a maze, and it knows that uh, for a particular maze, there's a door over at some point, and there's a wall surrounding it. So if it is able to detect the edges of that door, it knows exactly where to travel through, and therefore it knows that where it has to like move ahead. So that is an example of how the very simple task of edge detection could be very useful to a robot, and it might help it in localization. It might help it in solving its other objectives of clearing that maze. Like the entirety of computer vision is to like trying to think about certain features which might solve your particular task. That particular task is going to give you some meaningful information about the environment. So like what meaningful information did we get? We got the information about where the door is. So once we have that kind of information, we can proceed to using that information, and we can like just solve the maze by going through that door. So like computer vision is just these three steps: getting the input image, performing certain operations, getting a feature, and that feature tells you what to do with the environment. So the following slides basically give you the entire mathematics about what goes into building an edge detector. So in these two slides, the first step to building an edge detector would be yet another convolution operation, which would be the operation of removing noise from an image. So by removing noise, I want you to like think of why removing noise is something which is important in the first place. So if you have a lot of pixels which should not ideally be present in the input image, they can give you a lot of fake edges in that image. So it is really important that you remove all of the noise and you make the image somewhat smoother, so that only the sharpest and the most important of the edges come out after all that processing which you're doing. So for removing noise, we do something which is called convolving with a Gaussian operator. So I'm sure you would have studied two-dimensional functions by now. So the Gaussian operator is something like this. It has a maxima. So I'll just read it out for you. Gx of y is equal to 1 by 2 pi sigma square exponent of minus x square plus y square divided by 2 sigma square. So observe that it has a maxima at 0, comma 0. So when I have to build a kernel on the basis of it, I've built a kernel similarly, like 1 to 1, 2, 4, 2, 1 to 1. The maxima is at the center and the whole is divided by 16. So like that is the Gaussian kernel. I do not want to like magnify the values of the pixel after convolving. So I'm dividing it by 16. So when I multiply this Gaussian kernel, when I convolve the original image with this Gaussian kernel, I'm going to get a weighted sum of all the components of those pixels. So like the first pixel is going to get multiplied by 1, the second pixel by 2, the third by 1, the first pixel on the second row by 2, the central pixel is going to get multiplied by 4. Therefore, I'm going to get a weighted sum of the pixels but the central pixel is going to have the maximum emphasis on it. So why do I want to put maximum emphasis on it? So like this go to a very simple assumption. It goes back to a very simple assumption is that the real value of that pixel is given by the central pixel, and all the other values are something which might be noise. So if you so that assumption holds true when you apply that convolution across the entire image, and you can see that it kind of averages out that entire image. So like the averaging definition of blurring, making values more similar to each other, you can see that that image was very sharp earlier and it is now rather blurred. And if I increase the standard deviation, which is a parameter, the sigma parameter and the Gaussian operator, so that it becomes more and more blurred. So Gaussian smoothing helps eliminate the noise. The larger the sigma, the greater the smoothing of it. So once we've removed the noise, only one step remains of finding of before we are able to find our edges would be to take derivatives from take derivatives across the image matrix, and that is going to give you the edge. So if you want more reasoning about why this is going to work and why this is going to give you an edge, try to work from the definition of an edge. So since an edge represents a sudden change in the values of nearby pixels, what information does it give you? It tells you that there's going to be a sharp change in the first order derivative of that function because there's going to be a sudden change. So, and to accommodate a sudden change, there has to be a maxima of the derivative for those pixels. So, like, I want you to think back about how to calculate that particular derivative. So, from this convolution operator we had seen over here, 1 minus 1, 2 minus 2, try to visualize it like fx plus delta minus fx. So what is this giving to you? It is going to give you an approximation of the derivative of that particular matrix. So for all the points when you've calculated that derivative, it is going to be maxima only for the points which have an edge, because we talked about there is a sudden change in the value of nearby pixels. So once you have all those points where there's a maxima in the derivative, you can apply a technique called thresholding. So what thresholding is that it makes all the values above a certain threshold equal to certain value, and all the other values equal to zero. So I could say all the values above so like after doing the derivative convolution, I'm going to get the derivative matrix of the input image, and on that image I'm going to apply thresholding. So once I've applied thresholding to that image, I'm going to get exactly where the edges are, and that is going to serve my purpose well. So I've summarized this as well on the slide. So the gradient points in the direction of most rapid change intensity. You can calculate that by the gradient of this image. Using this, we can calculate the edge strength, which is the magnitude of that gradient. And by applying a threshold on that edge strength, you would be able to know where are the true edges and which edges need to be discarded. Okay. So this been a lot of maths, and I really don't expect you to like grasp it all in the first watching of this video. But what I want you to take away from this segment of the lecture is about how beautiful this task of computer vision is. Like you started off with numbers, and then you went on to like identify. Okay, so I need to get certain features from those numbers. I need to know where the edges, where the door on the wall is, and to get that, you looked at certain methods called image processing, which are basically making changes to the image matrix so that it becomes more useful to you. And once you've done those kind of changes, you're able to get really magnificent results. So like from the input image, you're able to get an image which only has the edges. And basically you're able to do a lot of stuff like removing noises, like finding the derivative of the image, etc. So like just take away these three things from this lecture is that computer vision is the study of matrices of the images. If you apply image processing methods, you're going to get certain useful features. Those useful features are going to help you solve certain problem in the environment. So right now I'll be handing over to Aryansh. He has some demos ready for you, and he'll be showing you in code about how someone could actually do these kind of operations. So, good luck and bye.
So now, as we all have gone through the introductory theory, I would now like to show some of the applications through the code in Python. So following will be the topics that I would be covering today. And the topics to be covered will be, first we would start with reading an image or inputting of image in a program. Then we would see how an image behaves as a numeric array or as stored as matrix. Then we would see that the red, green, blue components of the image, or to say RGB channels of image. And then finally we would be playing with pixel, that is doing inversions and color contrast by changing the values of pixels. Okay. So for information, pixels are the block of this matrix, like they are the particular like ith comma jth element of this matrix. Okay, so let's start. So along with this, along with examples, I would also go through the code so that you can understand it better. The code is simple and easy to understand. So now here, these 4 lines, I'm importing the Python libraries. The PIL library stands for Python Image Library and used for certain functions that are associated with image in Python. The NumPy library is associated with numerical operations in Python, and the matplotlib is associated with graphical functions in Python. And import CV2 is the abbreviation for OpenCV. And here we will not be using much of the functions on OpenCV. I've just used this for writing these images that we would generate into the drive. Okay, so to get the output and input, I've used my drive, and hence I have mounted this drive with this Google Colab. Okay, so let's start. So I would be reading an image of Steve Jobs, and this would be the reading and writing would be associated with this folder that I have. So I would be reading image from this image, that is Steve Jobs from, and all the output that we get will come here in this image folder. Okay. So firstly, I give the path of the image that is in my drive, and then store it as an IM variable that stands for image. And then when I run it, so first of all, I print the image shape. So as you can see, the image shape consists of 3 components, that is 600, 599, and 3. If you closely see this, so these 2 values are roughly same. So these stand for width, height, and the channel. I would tell you more about the channel later on, but as you can see now, that these 600 corresponds to the 600, 599 correspond to the width and height of the image. Then I have printed the type of the image. So this, as told you before, that this image acts as a NumPy array, or you can simply understand this as a matrix or a computer, and that is why its type is a NumPy array. And then finally, these 2 functions are here for the image. I have plotted the image from these 2 lines. Okay, so moving on. So to see how this image is behaving as an array, what I've done is I've taken the first 10 values of the columns, then next 10 values of the rows, and correspondingly the 0th channel. These all are here as indexes of the array. So when I run it, so as you can see that this image, the first, this image has 600 columns, 599 rows, and 3 channels. What I've taken is the first 10 columns, the first 10 rows, and the first channel, that is corresponding to the 0th index. And you can clearly see that how this is behaving entirely as an array, or you can say matrix in mathematical form. And it contains, you can see these values numeric, these are integers, and these values range from 0 to 255. Okay, so moving on. So here, if I run this cell, what I've done is first I have printed the image shape, that is as before we saw. Then what I've taken is I have performed array functions for this image. Now you can understand this image. The computer understands this image as a matrix form. So you can directly access its components from the I, j values, that is 100, 150, or any such value. So what I've done is I have accessed the 100th column and 150th row. And since this is a 3-dimensional array, it contains 3 values for every width, for every I, j value. What I've got is this. For this line, I have got this. So this contains 3 values, 227, 193, and 183. To understand it better, I have also written it. The above example shows the value at y, x, that is 100, 150. That is the 100th row and 150th column of pixels. As mentioned, the colors of this array would be using the imRead function that we have used here. So yes, so by default, the function, this would be containing the RGB values. So here, so the result is RGB 227, 190. To better understand it, let's run this cell. So what I've taken is, instead of simply taking this value, I have taken this value into 3 separate parts, that is red, green, and blue. And if I print all the 3 values independently, then you can see that the red value is corresponding to 27, the green value is corresponding to 193, and the blue, standing for B, is the 181 value. For this, my idea is like you can better understand this from this image. So an image consists of three separate layers, and that is what I am calling the channel. And each separate layer is consisting of this red channel, the green channel, and the blue channel. That is what we are referring to as RGB image. And for each of this channel, we have a corresponding numpy or a matrix. So the matrix that you are seeing here is one of the layers of such R, G, or B. And similarly, for this 100, 150th column, I have received these three values, which you can see here: 227, 193, 181. Similarly, so all of this, like the basic idea to show that how an image behaves for a computer. It is simply a numpy array or a matrix, and that matrix has three layers, and that three layers correspond to the red, green, blue values. Okay. So now moving on to our next topic, we have covered these topics. So, so now let's see that how this red, green, and blue components of image behave. So what I have done is I have created a array that is like I have copied my original image array into a new variable called image underscore r. And what I have done is all the rest of the channels, that is the green channel and the blue channel, I have put them the value 0. Similarly, what I've done is I've created a variable image dot underscore green and given the blue and the red channels the 0 values. So the R channel corresponds to the 0 index, the green channel corresponds to the 1 index, and the blue channel corresponds to the second index. So 0, 2, that is red and blue channels have been given 0 values. Similarly, for the blue channel, I have given the red and the green channel 0 values. Now what I have done is I have concatenated these three arrays, that is red, green, and blue, and then printed them, or you can say I have written them to the drive, saved them to the drive. Now if I run this, so there is some error here. Okay, so let me just correct this. Okay, so having done this, I think I should get my file in this drive. So now you can see that I have got the three images. So this corresponds to the red component of the image, this corresponds to the green component of the image, and this corresponds to the blue component of the image. Mixing these three images would give me the original image. So I hope that you have got an idea of how an image behaves for a computer and what are the components or what the image is comprising of. Okay, so now we will be playing with the pixels. So as you can see that the image comprises of just numbers for a computer. There's nothing else. So now we will be playing with the pixel values of these images. So as I told you that the pixels value range from 0 to 255. And what I have done is I have inverted the image. Like I have subtracted the original value of the pixel with the 255 value, and that is what I am calling inversion. Negative positive inversion can be generated by subtracting the pixel from the maximum value. And then I have saved this image to the drive. If I run this and go to my drive, so you can see, so this looks like a bit ghostly. So sorry for that. You can see that the colors have been inverted. The light colors have turned into dark, and the dark colors have converted into light. Like you can completely see from this. This is the dark, this is the light, and here you can see the difference. So what I've done is I've inverted the image. And what I've done for this function, I've just subtracted the original value with the maximum threshold. That is 255. Okay, so this was inversion, and now I will show you some two more simple functions. So the image, as I told you, consists of simple numeric values, and now you can play with these numeric values. You can divide, multiply. So like what I have done is here I have divided 32 and 32, and then divided 122 into 122. And now if I run this file, so these are simple numeric functions that I want to show you that how you can play with images in computer vision. So now if I load this, so this, you can see what I have done is this is my original image, this is my second image, and this is my third image. What I have done here is I divided the value with 32 square, and for the next image I divided the value with 128 square. And as you can see, the intensity of the pixel has reduced sharply. So this is the original image. This is the second image for which I have divided the 32 square, and this is the third image for which I have divided the 128 square. And as you can see, the intensity sharply decreases. And finally, now what I've done is, this was like simply division. To show one more application, what I've done is, here is I've first multiplied the image with, divided the image with 255, and then this corresponds to the power. So I have exponentiated to the 1 divided by 2.2, and then I have changed these values for second image. And now if I run this, let's see what was the result. So here is the image. So as you can see, this is my original image. This is the image. So I have concatenated like this. So the IM corresponds to the original image. The first image here, this image is corresponding to this value. So we can see that this image is lighter than this image is darker than this. So what I've done is, this is to the power of 1 by 2.22, and this is raised to the power 2.2. The overall value of this array, the individual elements in this array would have more value than the original one, and this elements of this array would have value less than that of the original one. So hence you can see the result. This is a darker one, this is a lighter one. Okay, so this was the example one, and the basic idea of this overall program was to go through the simple applications that can be performed with images. So here I have not performed like what you have studied, convolution, kernels. I would show you in a later example that would follow after this. The core idea of this example was to show how to input the images and how does the computer understand the image. So it understands the image completely as numerical arrays or metrics. And since it understands the image as metrics, we can perform simple functions like simple algebra function with the matrices, and we can get the corresponding result in this with the images. Okay, so having understood the basic concepts and gone through the applications, now let's move a step ahead and go through more examples. Okay, so this is the second example file I have created, and in this I would be covering 3 topics. So the first one would be the grayscale image, the second one would be convolution and kernels, and the third one would be edge detection. Okay, so let's start. So this is as it was in the previous one. We have imported 4 Python libraries, and I have attached the drive with this code. Okay, so I have used the same stage of image as in the previous example, and if you run this, so it is the same image, and you can see the same dimensions and the same type. Okay, so I have inserted the image into the program, and now let's see what is a grayscale image. So as we saw in the previous example, that an image consists of 3 layers, that is the red channel, the green channel, and blue channel. But what if I do not need these 3 channels, or you can say I want to convert these 3 channels into a single channel? I don't need these 3 separate channels. I want to convert the information of these 3 channels into a single channel so that I could get a 2D information from my originally 3D information. So one way to do is to use the concepts of weights, and for each of the RGB values, I assign a unique weight. Weight corresponds to the values, and then multiply with them, and then can generate a 2D image. To better understand this, I have used this concept, I have used this image. So you can see that originally my image is a multi-channel image. It consists of RGB values. So IR, IG, IB corresponds to the intensity of the image at XY location. Okay, but now if I multiply these weights that I have got, these weights can be changed. If I multiply these weights with these 3 values, then I would get a single number, and now I would put the single number corresponding to the XY location, and that is the procedure how I can get a 2D image. Now if I run this, so you can see the size of the grayscale image that I have obtained is 600, 500. That is, this is a planar image, and the 3 channels that I originally had have now been removed. Now let's see what is the output. Okay, so this is the image that we have got, and you can clearly see. So the name of this grayscale image is because the weights that I have chosen make this give it a grayish whitish shade. Hence the name grayscale image. And this is very beneficial because performing functions with 3D vector, so it is for the three-dimensional vector, is a bit tough and can be complex and time consuming. To make my process faster and efficient, what I have done is I have associated the weights uh, corresponding to each of the RGB values. In short, what I have done is I have converted the original information of the image into three layers into a single layer information. So that was the concept of Grayscale Image. Now let's move on to convolution. So in the theory, we had gone through the convolution. Now I would just briefly overgo through it. Okay, so this is the function of convolution, which intakes an image and a kernel. Okay, and here I have called this function. So now let's understand briefly that what is the kernel and how convolution has been used. So I have used this image to make you understand better. So this was my image. So also here I have used 2D convolution, that is the input image would be 2D, and this grayscale image was a 2D image. So for all of these convolutions I would be using my grayscale image. Okay, that is one two-dimensional and it contains only one channel. Okay, so this is, you can assume that this is my grayscale image and this is one dimensional. So this is one component of the input. The second component of the input is this kernel matrix, and this kernel matrix has values in such a way that it decides what information I want to obtain. You would better understand this when I will show you the example of edge detection, but you can understand the purpose of this image is to show you that if I move this cell or the kernel one by one over this image, then I would be getting a unique value for each of these 9 pixels. Like how the process would be done is like 0 into 105, with then plus minus 1 into 102, plus 0 into 100, and so on. Adding all these values and multiplying each of these values with the corresponding image matrix, I would get a unique value. Oh, sorry, not unique. I would be getting a value, and then this would be my output matrix. Okay, so now let's see an example. I have created a kernel whose values are as shown. So it is 0, minus 1, 0, minus 1, 5, minus 0, minus 1, 0. Now you would ask, why these values? So I have written is that this kernel is used to sharp the image. So how can I sharp the image? That this purpose, this would do, what it would do is, it would create sharp borders of a pixel. And that is like, you can see all of the values are 0 and negative, and the center value of the pixel is a positive and has a significant difference as compared to the rest of the value. So what it would do this, it would highlight the center value of the neighboring pixel, and hence it would sharp the image. So let us run this and see the results. So it has run. Now let's see. Yeah. So this was my original grayscale image. This was my original image, and now this is the image that I have got after this sharpened. You can clearly see the difference between this and this. This and this. You can clearly see that this image is a sharpened version of this image, and that is why the use of kernel. So now you can see like how important kernels can be and what different applications I can use. So I have used this kernel for sharpening the image. Similarly, I can use this kernel for blurring the image. I have used appropriately, like the values would be used as per the function. And if I run this, so this is the blocks blur. So this is the blurred version of the original file. So similarly, like this is a Gaussian blur, this is a box blur. There are different types of blur that depends on the type of task that you want to perform, and based on the type of task, you can give the kernel corresponding the values, and similarly, you can perform different functions. So finally, I would conclude this with the edge detection. So edge detection forms is very common function that is used in computer vision, and is one of the crucial, or I could say the most one of the important functions as well. Because if because like in robots or in in simple certain applications, I want to highlight the end of an image. And what would decide the end of an image? What would highlight that this image, like for example, if in a crowd I want to identify humans, so the very first step would be to mark the boundaries. And if I talk about the boundaries, then I automatically talk about the edges. And hence, so this is a very simple idea. There can be many ideas in which this edge detection can be used, and that is why it is very important. So for edge detection, there is no rocket science. Simply, I have changed the kernel values. Now, if you observe these values, what are these? I have highlighted the upper values of the associated pixel and subtracted the values below the, or you can say in the second row from the from the zeroth row, and this would highlight the edge of my image. So now, if I run this, you would better understand this with the output. So here is the output, and you can see that how I have detected the sharp edges of the image. So seeing the result, I'm guess that you must have felt be surprised and now amazed by the effect of the simple function that it has on the input image. The input image was a simple image of Steve Jobs, and what I've obtained is the edges of the image. It somewhat appeared an artistic. So overall, the idea is that we can perform very interesting function, and it is simple algebra. If I were to state in a mathematical form, it is very interesting. So we first started at how to take an image. What is an image? Image is simply a numeric array or matrix, and with this you go on to perform different things or based on what you want to get, and all of the algorithm based are simple algebra. Okay, so now I would conclude this lecture. Thank you and have a nice day.